Hi, I'm Tim Dallas. I'm a professor at Texas Tech University, and just want to thank you for joining me today to talk about micro and some nano devices. Before we get started, just to tell you a little bit about myself, I have a educational background in physics. Undergrad, I went to the University of Chicago, and for graduate school, I was here at Texas Tech University. As I said before, now in electrical and computer engineering, but for, I guess, a 2-year span, I was in Austin. I worked for a photolithography company. Photolithography is used to, in the process, to make computer chips and also some MEMS devices. And I also did a research position at the University of Texas. So since I've been at Tech, my research has focused on MEMS devices. As you'll see in the presentation, we'll talk about what those are, and actually have a startup company that is commercializing some of these devices, and we'll once again talk about the technology that we've put out there. And finally, just to mention that we do use commercially available MEMS devices for some special projects, and the main one right now is to try and prevent and eventually predict the instability of geriatric patients and try and prevent them from falling if at all possible. So it's one example of how MEMS devices, these MEMS-based sensors, can be utilized to try and to help people. All right, so I've entitled my talk today "Micro Machines," and hopefully you'll have a good idea of what that means once we get through this presentation. So micro and nanotechnologies are very important. We've already seen over the last 20 or 30 years some very important devices and technologies that have been developed and actually made their way into the marketplace. So just from personal computers and phones and medical devices, there's just a whole host of technologies that have been made possible because of the development of micro and nanotechnologies. There's still many things that can be done and need to be done, and that's why the U.S. and certainly many other countries need engineers and scientists that not only know something about micro and nanotechnology, but can actually harness those concepts, those ideas, and turn them into real-world solutions for a wide variety of problems that span medicine and energy and even education. So just to give you an idea of the range of where, I guess, the size range of these technologies, I have this little graph that takes us from the macro world, where we have buildings and people that are in the meters to tens of and even hundreds of meters in dimension, down into the micro and the nano world. So a lot of the devices that we'll talk about today are usually a little smaller than some of the bugs you might encounter, such as an ant, and kind of extend down into the regime of some of the cells in our body, like red blood cells, which are on the order of about 5 micrometers in diameter. We'll just briefly talk about some nanotechnologies, which actually extend all the way down to the atomic level, where individual atoms or very thin layers of atoms play a very important role in the properties and the operation of some of these devices. So once again, just to give you another idea about the scale we're working at, we'll start here with human hair. Use this quite frequently to try and explain the size, scale of some of the devices we're dealing with. The average human hair is about 50 micrometers in diameter. Once again, a red blood cell is about 5 micrometers, so about 1/10 the diameter. We'll be looking at some micro machines that have gears and other mechanisms that are on this scale. So for example, there's a micro gear right here that's about 250 micrometers or 1/4 of a millimeter in diameter, and you'll see some small holes that go through the surface. Those are about 2 micrometers in diameter, so even smaller than the red blood cell. So red blood cell would not be able to pass through these small holes in the gear. So we can go even smaller with technology, and certainly you probably heard the term transistor. Transistors are what make up the computer chips that we know and love and rely on a daily basis. In this day and age, a computer you can buy off the shelf, just a standard computer, is going to have a computer chip on it that has over 1 billion transistors on it. And this chip is going to be probably on the order of 1 centimeter square, about the size of maybe one of your fingernails. So in order to have so many devices on such a small area, each one of these transistors has to be very, very small. So what I have here is what's called a cross-section view of the business end of the transistor. This is kind of cutting through the heart of the transistor, and we have a zoom-in view of the gate and the channel of this transistor. So using very specialized and very expensive electron microscopes, we're able to actually see all the way down to nanoscale and even be able to see individual atoms. So most computer chips are made from silicon, and here we can actually see individual silicon atoms in this array. There's other atoms that are seen here above it, which are kind of more disordered than the crystalline silicon we see at the bottom. But that just gives you an idea of how small some of the components of these devices are. They go all the way, of course, down to the atomic level, and the atomic level is very important to the operation of these devices. So as I said earlier, a lot of my research is in MEMS, and MEMS is an acronym for Micro-Electro-Mechanical Systems. Undoubtedly, you've used some technology that incorporates MEMS devices, whether you may have realized it or not. One of the primary areas you'll find MEMS devices is in some gaming applications. So Nintendo used MEMS sensors in their Wiimote. So in the main part of the Wiimote, there's an accelerometer, and there's also a Motion Plus add-on sensor that actually has a gyroscope in it. And those devices are what allow you to control the action on the screen, allow you to interact with your games. A similar accelerometer is used in cars, and this is what tells your airbag when to deploy. So if you encounter a fast enough stop where you have a high deceleration, then the accelerometer chip senses that deceleration and sends a signal to the steering column, which detonates the airbag, and very quickly, within a fraction of a second, there's a big white pillow right in front of you that hopefully has protected you from hitting the steering wheel and the windshield. So this is one of the main examples of a MEMS sensor that has really led to some life-saving and injury-saving outcomes, and has really been quite important to the safety that we enjoy in automobiles. Another area where you'll find MEMS devices is in video projectors. Texas Instruments developed a device called the digital micromirror device, and this is what the chip looks like. This is approximately 1 inch on a side. These devices are used in rear projection TVs, some video projectors like you'd find in classrooms, and even in some handheld video projectors called pico projectors. In order to render the image, there's an array of micromirrors, and this is another electron microscope image looking down on those. Each one of these micromirrors is about 10 micrometers on a side. So these are very small, allows you to put on a standard XGA array over 800 or about 800,000 of these micromirrors. Here's kind of a little diagram showing the mechanism of this micromirror. Essentially, you have aluminum plates, which are the mirrors, and they're controlled electrostatically, and they flip back and forth, either sending light out of the projector or sending out a dark pixel. By either using light-emitting diodes or a color wheel, the video projectors add color to the image. These micromirrors move very fast. They typically flip back and forth 3,000 to 5,000 times per second. These can be scaled up, and some HD TVs and movie theaters actually use chips that have over 2 million micromirrors on that one chip. So just to show you a few more, or give you a little bit more information about these MEMS devices and the way they're fabricated, they do leverage computer chip manufacturing, so the same technologies, the same systems that are used to make computer chips are also used to make MEMS devices. So these include thin film deposition, where you're depositing microscale, and even nanoscale layers of materials. Etching is how you create the individual micromirrors, so you're removing material. Photolithography is used to pattern, which gives basically the dimensions of each of the structures that go into your device. And then once it makes it through the fabrication facility, there's additional coating, dicing, and packaging steps that allow these systems to be utilized in consumer products like the video projectors and airbag systems. Here's another view of the digital micromirror device. You can see the hinge in the center and a cutaway of the micromirror. Here's another image of an accelerometer, and just one brief example of how lithography is done. So when you start thinking about education and career options, people have many different interests. And the cool thing about micro and nanoscale technology is that it really spans many, many different engineering and science disciplines. So I have a list here of some of the main engineering disciplines: electrical, mechanical, chemical, bio, that are directly in the the development and application of some of these MEMS devices. Certainly a ton of work goes into material science, developing new materials that function the way we need them to for these devices, and certainly utilizing well-known devices in maybe new ways. So it's great to have a good background in physics and chemistry and certainly biology if you're looking at devices for medical applications.
Dr. Dallas, I'm sorry, can I ask you a question? When you started out and you went into engineering, did you know you wanted to do electrical engineering? Did you know what area you wanted to specialize in? How did you come to know about all of this or be interested in this?
Well, as I said earlier, my background was in physics, which gives you a good basis for at least some fraction of these technologies. When I worked in industry, I worked for a semiconductor equipment company, and so it's one of the tools that is utilized to make these devices. It's just one part of the overall process. And then when I did research at the University of Texas, I continued to do some photolithography research. But when I got the position at Texas Tech, I was pretty sure I didn't want to just do photolithography, and I was pretty sure I didn't want to do standard transistor work. And so it was a time where where MEMS were just kind of becoming a little more mainstream, and I was really intrigued by some of the technologies that I saw. And so I essentially just pushed out into a new area research-wise and got into the MEMS field, and without really actually knowing exactly what I was going to do, but successfully got some funding with some colleagues to do some work in the MEMS area. We developed a 3-course sequence in MEMS, and so we've now been teaching the MEMS classes since 2000. So now I guess it's been, this is essentially the 13th year we've taught these MEMS classes, and so it's been really, I guess, a lot of fun, very interesting, very challenging, and to be able to combine the what we do research-wise with what we do in the classroom, and there's a lot of overlap between the two. They've really kind of fed back each other and allowed us to make some good educational advancements in MEMS and also some good research advancements in MEMS.
Thank you.
All right, so when we are developing our MEMS devices, and in the next few slides you'll see some examples of this, we go through a number of steps, and this slide just kind of gives you an overview of some of the primary steps we go through to develop some new devices. And that's one of the things that we really enjoy doing is having an idea and developing it into a working device. So we usually start off by designing, simulating, and modeling the devices. We'll use AutoCAD to design a lot of our devices, and that's kind of shown in the figure here. We also use some computer modeling and simulation that allows us to apply essentially physics to the devices prior to actually making them. Making these devices can be very expensive, very time consuming, and you don't want to make any mistakes because the problem can be problems that cost you tens of thousands of dollars and maybe a year of time. So you want to use computer tools as best as possible to try and make your design as good as possible before you actually commit it to the fabrication process. So once again, we use AutoCAD-based tools to design our devices. There's some additional software in AutoCAD that allows us to once again look at the model, in this case look at a cross-section of one of our structures. It allows us to check for any problems that we might have with our design. The way we operate is we design here at Texas Tech, and then we send the designs to a national lab. It's Sandia National Labs in Albuquerque, New Mexico. They have a fabrication facility that probably has a couple $100 million worth of tools, very experienced and qualified people that actually turn our designs into devices. These chips are then go through a packaging process. Sometimes we like to test them first before putting in the package. So we'll use electrical probes that are shown here to actually bring power to these devices and check for functionality. But eventually we then put the chip into an electrical package. This particular chip also has a window on the top of it. The window protects these very small devices from particles and people. We then incorporate this chip into an overall system. So you see the chip here. We've put a quarter here next to the chip, so you have some idea of the scale. We use a compact digital microscope usually to image the devices on the chip, and we've also developed a power supply that allows us to control these devices through the computer. And this final slide, this image, you can see there's a student that's working on one of our chips, and you can see some of the micro devices on his screen. All right. Once again, to kind of illustrate how small these devices are, we use the US penny, and here is the design, the AutoCAD design layout of one of our chips. At this view, you really can't see exactly what's on the device, and so we're going to zoom in closer and closer, and you'll get a better idea of some of the devices that happen to be on this chip. We'll show a couple times some micromotors, and I'm pointing to one right here. This is about 1 millimeter in diameter and actually produces rotational motion. The diameter of this micromotor is similar to the 0 that appears on the date for this particular penny. As we zoom further in, you can get a better view of the devices on this chip, and it turns out that this device in the top left corner is actually a microClock. So there's a number of gears that allow us to transmit the rotational motion from this micromotor to the second, minute, and hour hand. So there's some additional devices on the chip as well. And if you look at the scale here, once again, the entire chip is about 6 by 3 millimeters. We're once again utilizing an electron microscope to give you a better view of these devices. Once again, on the left-hand side is the micromotor. There's gears that transmit the rotational motion, and you can see the second and the minute hand. If you look closely, the second hand for this device is actually the Texas Tech guns up symbol that is sometimes used, I guess primarily at sporting events. Here you can see a little closer view of that. this index finger is on the order of about 10 micrometers across. Once again, all these little holes that are needed as part of the fabrication process that allow us to make these devices are about 2 micrometers in diameter. So in just a moment, as the video gets warmed up, you'll actually see this device in operation. So the micromotor is spinning, and you can see the second hand moving around. You'll see the minute hand click over one little click in a moment, and there it goes. And all these gears actually work and actually operate this device. So this is one of the first devices that we did, I guess now going back almost 8 years ago, and we're very excited when this device worked. So a couple years later, as we started to think about what we could do, what additional things we could do with this technology, we thought about what if you could essentially shrink down some of the lab apparatus you'd find in a physics lab if you shrink it down onto a chip. So certainly the world of computers has benefited from continuously shrinking down the size of transistors. When the first computer chips came out, there's just maybe hundreds, maybe a couple thousand transistors on it. I said earlier, now we're over 1 billion, sometimes 2 billion transistors. So being able to shrink down some of these technologies has really allowed us to make some important gains in many areas. And we thought, well, what if you could do the same thing with some of these movable devices at the microscale? So instead of having a room full of relatively expensive lab equipment, let's shrink it down and put it on one chip. So this is where the concept of class on a chip came about. This technology can be used to teach a variety of topics that include many physics concepts, many engineering concepts, and even some micro and nano technology type concepts. We wanted to design the system to be accessible to many users. We like to see professors in universities and even teachers in high schools and high school students be able to utilize this technology just as easily as they utilize their smartphones or other lab equipment. In order for it to really be valuable, it has to be interesting and fun to use, it has to be cost effective. If it's too expensive, obviously people can't afford it, and in many cases some of these technologies we have to utilize it to teach things that are mandated by various state standards. So this is another view of one of the chips that we've made with this process at Sandia, and you can see that even compared to the previous chip, we've put a lot more devices on this particular chip. So it's the same chip area, but we've packed a lot of devices on there. So you can recognize maybe these micromotors again. Right here and here, we have some of what we call electrothermal actuators here that actually use relatively high temperatures to get motion from these devices. Here are some additional electron microscope images of these actual devices. So you see the micromotor again. This uses electrostatics to drive a ratcheting mechanism. We also use these electrothermal actuators that just work on applying current. We essentially send in current through these thin arms, and these heat up and move. The temperature that these get to is actually pretty amazing. They get to 600 or 700 degrees Celsius and back to room temperature very quickly. In fact, you can operate these at basically hundreds of times per second, or 100 hertz. And it's something you certainly can't do with your home oven. You can't turn it on to full temperature and back to room temperature hundreds of times per second. Because these devices are microscale, they actually take advantage of some interesting micro and nanoscale properties that allow you to switch them on and off very, very quickly. So we're going to take a little closer look at this MEMS chip. Here we have in the center of an electrical package. This electrical package, you see that there's these wires coming down. Each one of these wires corresponds to one of these gold rectangles, and each one of those gold rectangles has a very thin wire, gold wire, that connects the devices on the chip to the edge of this package, and then eventually to the outside world, and allows us to get power into these devices that allows them to operate. Here's a bigger view of the overall system. We have our chip. We have a board with a socket sitting at a printed circuit board, and what I'm not showing here is wires to connect this connection here to the power supply, and then this power supply is connected to a computer and allows us to have very good control of these devices. A lot of times we'll use a very compact digital microscope that has its own light source right here, and so this entire laboratory essentially fits into a very small area and can be easily transported. This is just one example of the graphical user interface that we've done using National Instruments LabVIEW software. So on the edge here we have voltage control and also frequency control. So those are really only the two knobs that you're using to control these devices. You can have, with the digital microscope, you can put the image of the devices that will be moving right on your screen. And we also have included a little chip map that allows you to see where on the chip you're supposed to be pointing your microscope so you're looking at the right device. Everybody loves doing labs, of course, and we've developed a few labs to go along with these devices. So just like you'd have a lab manual for your regular physics classes, you also have a lab manual for some of these devices on the Glass on a Chip system. And these labs we actually do in our MEMS classes here at Texas Tech. Typically we do 4 or 5 labs as part of our class curriculum in our first MEMS class. One of the other things we can do with this technology is, because we're using a digital microscope, we can actually stream the images over the internet, and we can actually allow external users to control these devices. So the LabVIEW interface can be basically on a remote user's desktop, and they can stream the video of the devices operating. So we have a system where in our laboratory we have our microscope and we have one of these MEMS chips, and we've had people actually utilize this system to do labs remotely. So we've had distance education students take the MEMS class, they log into our lab at Texas Tech and actually conduct the same labs that students would conduct if they were on site here at Texas Tech. All right, so we've talked a lot about the system. I thought it'd be fun to show one of the videos that Sandia National Labs has produced that kind of shows some of the additional devices that are out there that can be made with this technology. So we'll go ahead and show this. I'll try and talk a little bit about some of the things you'll be seeing, and then after this we'll show you a couple more examples of some of the devices that we've done with the technology at Tech. So once again, Sandia National Labs is a national lab and has this standardized technology, fabrication technology for making these devices. So here's another gear-based example. This might look reminiscent of a locomotive engine. So you have these two rods that are spinning those gears, and using this system you can generate some very high rotational velocities. This particular one is almost 150,000 RPM. And here we can see zooming up on those gear teeth. So if you didn't know any better, you might think that these are macro scale gears, but actually each one of those gear teeth is only about 10 micrometers in extent. Using these technologies, you can move light around. In some ways, this is a little analogous to the digital micromirror device, except this is a much larger mirror, and you see red light bouncing off that. There's a laser that's kind of coming from the right-hand side of the screen, and we're popping up the mirror and allowing the light to bounce into the microscope. So this could be used for positioning laser light. one of the basic labs we can do with this technology is just gears and gear motion transmission, and this is a vivid example of how a transmission can be used to change the rotational velocity of a gear. So as you see, we go further and further down this gear chain, it becomes harder and harder to see the motion of these gears. In fact, it's essentially you can't really see them moving as we get to the end here. So that's the power of transmissions, and allows you to take relatively high-speed motion and turn into some very, very low speed and very precise motion. All right, let the fun begin. So Sandia is kind of fond of seeing how, or at least using very small insects to interact with some of their devices, and this is, I guess you'd have to call it a bug merry-go-round. So we have this dust mite that's getting a little spin on that. That obviously was kind of a low-speed endeavor, and I'm sure you've probably wondered, do bugs get dizzy? And so now's your opportunity to see if that's the case. Got them pretty wound up. We'll spin them out a little bit more, and yes, in fact, it does appear that bugs do get dizzy when you spin them fast enough. So we have one final small friend that kind of illustrates how robust some of these very small structures are. So this bug is actually crawling directly on these devices. It'll pull on and kind of strum those what are polysilicon beams, and actually you'll see at the bottom here, whoops, kind of really pull one and they survive. So it's kind of amazing how robust some of these structures can be. All right, so we've done some devices also that we find kind of interesting, and we'll show you some videos of those in just a moment. The first one is a micro bicycle rider, and then we also have a micro dragonfly. So each one of these devices we can use for educational purposes, but they also do allow us to do some additional research on how some of these devices behave at the micro scale. So we're going to start off with our micro dragonfly. We have some electrical probes on the surface here that are applying power, and you can actually see the wings for this micro dragonfly moving up and down. We're actually using heating to cause the thermal expansion of these devices, and actually getting these the wings to flap off the surface just by probably about 20 micrometers. And then we also have our, I hope you enjoy the music, we have the micro bicycle rider with actual hinges and all these gears that allow him to look like he's pedaling the gears on his bicycle. So that basically concludes our presentation on these MEMS devices. I want to thank a lot of students that have contributed to this work over the years, and we've also received funding from National Science Foundation, Sandia National Labs, and also some internal funding from Texas Tech to do this work. So if anybody has any questions about any of the things that you've seen, my email address is tim.dallas@ttu.edu, and certainly I can be contacted if you have any questions. And also you can send some of these questions through Tracy Clanton Smith as well. So it's going to appreciate you guys tuning into this, and hope you learned something. Thank you.